Okay, hello everyone. My name is Michael Downey, Library and Information Services Coordinator here at the AWRI. And it's my pleasure to welcome you to today's webinar and also to welcome today's presenter, Neil Scrimgeour. A senior scientist with the AWRI and with a long history of overseeing technical projects relating to operational improvements, it's great to have Neil with us today to discuss the use of inline sensors to monitor sugar levels during fermentation. But before I hand over to Neil to tell us more, a couple of reminders on what you can expect from the webinar. As always, the format is a short PowerPoint style presentation, which is followed by a Q&A. The session is being recorded and will be made available to view via the AWRI website. For those that are new to webinars, it's important to remember that webinars are interactive and that there are a number of ways that you can get involved. To ask a question, please type into the question section of your control panel in the bottom right corner of your screen. For those with access to a microphone, there's also the option of speaking directly with our presenter by clicking the raise hand button, which is located in the top left section of your control panel. If you prefer to ask a question via email, please do so at infoservices@awri.com.au. Feel free to send through questions at any time, and once we get to the Q&A, I'll send as many questions through to Neil as possible. And just finally, if you'd like to get involved through Twitter, please use the Twitter handle @_AWRI. Okay, that's enough from me for now. I'm just going to hand over to Neil.
Thanks, Michael. Good morning, everyone. This morning I'll be talking about process fermentation monitoring technologies, specifically those related to monitoring of Baume during fermentation. So most of the subject matter this morning is taken directly from a One Australia funded study that was initiated back in 2014. It was a one-year study to screen viable process monitoring technologies for fermentation and to run subsequent field trials. So there's obviously many areas of winemaking that can benefit from process measurement technologies. Obvious benefits being that they give us the potential to streamline processes, reduce resources, predominantly labour around fermentation, and allow us to gain better control of the processes involved. Fermentation is often a bottleneck, and others in the process, but fermentation is or can be particularly challenging during vintage, can utilise significant resource, again quite heavily labour dependent, and obviously it's a natural process, so it's subject to a degree of natural variation, different fermentation rates, and issues with slow or stuck ferments. So technologies that allow better control of that particular process give us the ability to do things like improve scheduling, minimise quality downgrades, and improve throughput. So as a process, fermentation is fairly simple. It's the conversion of sugar to ethanol. Many factors can influence the rate of that process or how effective that process is. There's obviously a number of different inputs. On the left-hand side, we tend to monitor on temperature, or most people in the industry tend to monitor temperature, other than Barmay, in terms of chilling, and obviously as an output, the resulting temperature from the ferment as it proceeds is obviously another area of focus. We don't tend in the industry at the moment to focus on too many other aspects, but that's something that's starting to change as more technologies become available. In terms of process monitoring, the wine industry is still not particularly sophisticated. This is probably a good example, probably the best example in the industry of where this sophistication is relatively high. So this is an image from the experimental winery at UC Davis in California. So a series of 200-litre vessels set up with automated sampling, monitoring of Baume, and temperature, and all data is wirelessly transmitted back to a central control point. Like I say, this is a relatively high level of sophistication, and most wineries are nowhere near this, but the technology to achieve this type of thing is starting to become more cost effective and more available. Now, I said that most people monitor temperature during fermentation, and that's a big focus obviously, but it's probably worth bearing in mind that there is a degree of stratification that occurs in the ferment tanks as the ferment progresses. So I've just shown here some data. On the left is from a study undertaken in 2009. What we're seeing here is like a cross-section of the ferment tank, and the red area in the middle is obviously hotter than the surrounding areas outside. And you can see from that graphic on the top left, there's up to 10 degrees difference between the center of that hotspot and the external areas. The images that then go to the right and then below are images taken after the cap was plunged. So you can see once the cap's plunged, that hotspot tends to dissipate somewhat, but this image on the bottom right is taken a few hours after the cap plunge, and you can start to see that hotspot redeveloping there. The data on the right is taken from a refrigeration study carried out at the AWRI back in 2010. Shows a similar effect. There's quite a degree of difference between different points in the fermentation tank in terms of temperature. So that develops through the process, and it only starts to balance back out in this case where we increased agitation in the vessel. So it's just worth bearing in mind that although we do all tend to monitor temperature, it tends to be at a single point in the tank, and depending on where that point is and what's going on in the external environment around that point, it maybe only gives us a snapshot of the progress of the ferment. It doesn't necessarily give us the whole picture. Okay, so onto the Barmay Center trial itself. Two key aspects of that. The first, as I said, was to look at what sensors were commercially available that had the capability to monitor Barmay levels in wine fermentation. So the specific aspect of that was that they had to be commercially available. We couldn't look at sensors that were still in the development phase. And we screened the sensors available, selected a handful, which I'll go through in a moment, and ran performance field trials. Two particular sites we chose for this: Petaluma Wines in the Adelaide Hills and De Bortoli over in the Riverina. And one thing we decided to do quite early on was to focus on white ferments at Petaluma and reds at De Bortoli. And I'll show you some of the data from that trial as we go through the presentation. In terms of evaluation criteria, these are the key things that we looked at in terms of screening the potential sensors, and also to measure and monitor the performance of those sensors during the field trials. The technology options themselves, we looked at a number of different industries, particularly beer, a little bit of use in the soft drink industry as well for these type of sensors. Density measurement tends to be fairly predominant. Obviously with something like beer, working with a much cleaner process environment, so some of the technology options that are available and work particularly well in some other industries aren't necessarily ones that will perform particularly well in the wine environment, and again that's because of the nature of the wine fermentation and the matrix involved. Lots of research studies done on areas such as biosensors, which is the option at the bottom that we had a look at. Lots of use in beer and some studies done in wine, but again only sort of at a research scale, nothing in real commercial use. So it's an area of interest for us, but not one that we included in the trial. So those three sensors I've highlighted in blue are the ones that we took forward into the trial. We did also include the VS3000, which is an optical probe based on mid-infrared technology that was implemented at Bortley for the trial, but unfortunately we didn't capture any data on that particular sensor. So I'll just go through the three key sensors that we did get useful data on. The first is the vibrating fork. So this is supplied by Endress and Hauser, and it's based on the concept of an oscillating frequency applied to the fork, which you see at the end of the sensor there. And when the density of the medium that fork is inserted into changes, then the frequency changes. So as the sugar in juice is converted into ethanol, the density of that medium decreases and the vibration frequency increases. And then that is converted into a Baume reading. That's actually carried out in what they call a density computer, which is a fairly basic data conversion module. The second process sensor was the fermentrol. This is manufactured by a company called Cytec. The measuring principle here is osmotic potential. So you can see from the graphic at the bottom there's a ceramic membrane and there's a polymer that is semi-permeable that is used to measure the response based on how much sugar and ethanol is present in the solution that probe is inserted into. So that polymer expands or contracts depending on the sugar content in the ferment. And again, that pressure differential is converted into electrical signal, and that is then converted into what I've called an inferred Baume. So one important note with this particular model is that the initial Baume, when the ferment is started, needs to be inputted into the unit, and then that initial Baume is used to convert the electrical signal into that inferred Baume reading. Third sensor option is provided by Integrated Sensing Systems out of the USA. So the measurement principle here is very similar to the vibrating fork. We're looking at density measurements. Probably the key difference with this sensor is that it's a much smaller footprint. So all of the mechanical elements and the electronics are incorporated in what's called a MEMS, which is a microelectrical mechanical system that's similar to a microchip that carries all those useful elements. So much smaller footprint, not particularly process robust. It's certainly got lots of application for smaller scale and much cleaner environments. And I'll show you in a minute. In this particular application, we looked at a bypass loop to utilize this sensor rather than going into the ferment vessel itself. So this is the trial setup at Petaluma in 2015. So we've got a 6.5 kiloliter white fermenter. We've got the fermentrol and the vibrating fork, which were inserted through a modified door panel. We've got localized temperature probe here to provide temperature adjustment for the density measurement. That's done automatically on the fermentrol probe or within that unit. This is the density computer that I talked about. So the vibrating fork data is collected and converted in here, and then we've got a data logging unit here to collect the data from that particular sensor. The micro LDS sensor is situated in the bypass loop here, so we've got a hose connected to the sampling port, and we had a 2-hour measurement cycle on that, so sample taken every 2 hours through an automated solenoid valve and an inline filter. And we had daily samples taken by the lab for reference analysis. So I'll just run through a series of graphs to show how the sensors actually performed during 2015. I'll start off with the vibrating fork. With all these graphs, we've got Baume down the left-hand side, we've got temperature on the right-hand side, and number of days of ferment across the bottom. So the Baume data is in blue, temperature data is in red. Now we had some issues with electrical signal here early on, and we also had an issue with cooling failure on one of the jackets. So a bit of thermal runaway just to confuse things on this graph, but in this area here between day 4 and day 5, things started to settle down, and we got both sensors, the vibrating fork sensor measuring at a similar level to the reference Baume. And then from that point we see a bit of a divergence, so that signal from the fork jumps up, and we've got in the region of a 4 Baume offset between the fork measurement and the reference measurement itself. And we believe this is due to the fact that bentonite was added to the ferment tank at that point, and our assumption is that some of the bentonite actually settled on the fork of the sensor, and that damped the oscillation, therefore providing this offset. So essentially we're overestimating the level of Baume in the vessel, and we saw this pattern fairly consistently with the white ferments at Petaluma. This is just some example data provided to me by Yalumba Wines. So Yalumba looked at this sensor a few years ago, and this is just to prove that the sensor does perform as it should when bentonite is not included into the mix. So again, this sort of blue line here is the density probe, and the hydrometer measurement you can see in green, and the two track fairly closely all the way through. So the sensor is capable of performing in whites. The issue of bentonite is something that we hadn't foreseen, and it gave us an interesting insight into some of the practical limitations with some of these sensors. This is some data from the Firma probe. So you can see that for most of the ferment, it's tracking the reference Baume relatively closely. We do start to see an offset develop towards the end of the fermentation, and that offset is somewhat related to the way the inferred Baume is calculated from that initial Baume. It's a fairly complex algorithm that's used to convert the osmotic pressure, and it's affected by both the concentration of sugar and the concentration of ethanol in the fermentation medium. And obviously for most of the ferment, that inferred Baume tracks quite well, but we do end up with a slight offset at the end of ferment due to that calculation. And again, we saw that consistently with the white ferments at Petaluma for that particular probe. This is the data for the micro LDS, so the other density sensor. And again, this is one of the other issue we saw previously with the vibrating fork with the ferment itself, not sensor related. So if you look from day 5 onwards, you can see that sensor tracked the reference Baume relatively closely, probably as well as any of the 3 sensors did. We did, however, experience some issues with the sampling cycle that we're using. So we automatically sampled every 2 hours, but the volume that was sampled in the early stages here was not high enough to flush out the sample loop. So we increased that volume from about day 7, day 8 in order to make sure that we had a fresh sample going through the sensor at each sampling point. We did experience some minor blockages in this unit as well after 2 or 3 ferments, so it's probably more important with this one that some extra care and attention is taken to flush that unit out between ferments so those blockages don't build up over time. Now I mentioned the trial at De Bortoli with the reds being somewhat problematic. This is the setup that we had at De Bortoli. So we've got our mobile skid basically set up with the 4 sensors that we included in the trial over there. So 3 of them are the same, the vibrating fork, the micro LDS up here, and the Firma trial down here. And we've also got the optical probe, the VS3000 in here as well, and obviously some extra bits and pieces to try and reduce some of the solids content from the red fermenter. The sampling point was below the cap, but the agitation that was used on that ferment vessel meant that we had a relatively high solids loading coming through the bypass loop from that vessel. So everything was fed through the bypass loop, through all the sensors and then back in. And we did manage to get some reasonable data from 3 of the 4 sensors. The micro LDS was the one that didn't cope particularly well with that process environment, but the other 3 were all capable of collecting data during the ferment. The issue we had was with the filtration mechanism and the relatively high loading of solids in that bypass loop, and that was an issue we just couldn't resolve. But there are some plans, I believe, for the Bortley to trial that unit again, and maybe a couple of those sensors in 2016. So we only had the capability to capture a small amount of data for each sensor, or 3 of the 4 sensors that showed some capability, but I've got some additional data from other wineries to show that they are capable of monitoring Baume levels in red ferments as well as whites. So this is the setup that's used at Yalumba Wines. The sensor, which is the vibrating fork that's used, is actually housed behind this screen here. So they use the screen at Yalumba to protect the sensor from those high solids that are present in the ferment, and they've managed to get reasonably reproducible data over 3 or 4 vintages using that sensor and using this particular setup. And this is just some of the data that they've supplied to me. So again, you can see the data from the density probe, which is in red, tracking really closely with the reference Barmay measurement in blue. This is Firma trial data taken from St Hallett Wines in the Barossa. So they've been trialling the Cytec probe last year and this year. This year I think they had it in a number of different vessels. And again, they've seen reasonably good correlation between the reference Baume measurement and the measurement from the probe itself. You will notice though that we still have this offset developing towards the end of ferment, and that again was a consistent trend we saw in all of the ferments at St Hallett this year. So the probe was capable of tracking the trajectory of the ferment relatively well, but if you were going to look at the fermentrol probe in your particular winery, you may wish to introduce some additional sampling towards the end of ferment to just offset that issue. In terms of evaluating performance, there was a number of different aspects that we looked at. So in terms of the rating that was carried out through the Wine Australia funded study, we could really only focus on the results that we were able to get from Petaluma on the white trial. And we've used a relatively simplistic low, medium, high rating against each of those areas. So aspects in terms of how easy it is to install and maintain the sensor, how well the sensor performed in the process environment, and many other aspects. And this is just a quick summary of how the 3 stacked up just at Petaluma. So highest score is more effective. So the micro LDS actually came out on top, but there really wasn't a massive difference between those 3 probes. The vibrating fork in our particular trial underperformed due to the issues predominantly with the bentonite addition and the effect that had on the forks and on the sensor itself. But really there was not too much difference between the 3. There were pros and cons, as you would expect with all 3 of them. The micro LDS, the main thing to consider there or take forward from this is that it can perform relatively well, but it does need a bit of extra care and attention, and it's not a probe that you can stick into the ferment vessel. I think it's much better suited to a flow-through cell or a bypass loop configuration. Okay, so summary is there is really no silver bullet at this stage. The fermentation medium for wine is still a relatively challenging process environment. There are viable solutions out there, and there are process sensors that can perform effectively in the wine fermentation environment if, and it's a relatively big if, reasonable considerations given for how they're integrated into the process. In terms of future recommendations, we've suggested alternative methods for integrating the sensors into fermentation vessels, things potentially like retractable devices that can be moved in and out of tanks to reduce fouling issues, and utilization of more sophisticated data management and analysis tools. So obviously if you can get the data from these sensors into a central control system of some kind and maybe integrate that with things like the ferment simulation tool, which was developed through through the AWRI, gives you a much more powerful way of utilizing that Baume data and provides a very good early warning system for ferments that are likely to be problematic. Benefits for these type of technologies are fairly self-explanatory, I think, but obviously you can take more measurements more frequently, so there's more data to work with and there's more opportunity to act on that data and address potentially problematic ferments earlier on and reduce the risk and reduce the impact that those potential problematic ferments can have. Now, we've done some economic modelling on the potential benefits. The relatively conservative payback period, depending on winery size, is somewhere in the region of 1 to 3 years, and I'll just go through in a minute how we've come to those sort of figures. There's some other areas of benefit, like improved productivity and throughput. There are obviously things that you can potentially gain from implementation of this type of technology, but that it's very difficult to put a dollar figure on some of those things. So in terms of the cost-benefit analysis, we've categorized wineries according to the level of crush, as shown in the first table, made some assumptions in terms of number of tanks and average size, those sort of things. But if you look at the table at the bottom, you look at the winery size versus the payback period, as is the case with most of these type of technologies, the bigger the winery, the bigger the tanks, the shorter the payback period. So potentially less than 1 year for some of the bigger wineries, but you're looking at maybe 3 years for some of the really smaller wineries. So we made the assumption that if wineries were going to invest in this type of technology, they would look at 1 sensor per tank. Sampling would be once daily, or that's the assumption that that's what's carried out in industry at the moment. Energy, labour and wine costs, we indexed at 5%. In terms of the impact of the sensors, we looked at the lab analysis for Baume being removed as it would be in the short term, and we also looked at actual sampling of tanks, which I know goes on because tanks need to be tasted and sampled for other things, could potentially be decreased by 50% in the medium term. And we assume the incidence of problematic ferments per vintage was around 2 or 3%, and the impact of the sensors on reducing potential must or wine quality downgrades from problematic ferments could be reduced by 50%. So working with relatively low figures in terms of coming up with a payback figure. But just to comment on the sensitivity around the potential quality downgrade, this is just a graphic looking at the payback period for each winery size category. So this is for the small category, we're looking at about 2.8. For what we've called the huge, it's near to around 0.7 of a year payback period. But what I've overlaid on that is the impact from that potential quality cost downgrade. So we've assumed for a small producer, the cost of a lost ferment or a ferment that's had problems might be an impact of $1.50 per litre. But if the impact is nearer to $1 per litre, then that increases the payback period to close to 3.5 years. And the same with some of the other categories. So the medium category, we set our assumptions around $1 per litre as an impact factor, but obviously if there's a bigger cost impact, then that payback period comes down. If the cost impact is lower, then that payback period goes up. In terms of the future, we're keeping a fairly active watching brief on biosensors here because they do appear to provide the potential for a reasonably cost-effective solution going forward. There are a number of sensors that have been trialled in beer and wine. Like I said earlier, they tend to be based on glucose oxidase enzymes bound to an inert substrate, and the conversion of the glucose into gluconolactone produces hydrogen peroxide and oxygen, which we can pick up through an electrode, use a transducer to convert that into a Baume reading. This type of measurement principle is already in use in things like blood sugar measurement that are used for diabetics. But there are sensors that are available currently, like this Optiens sensor. They are nearing what I would say is commercial availability stage. So there's a tiny bit of validation work going on in the US with that particular sensor, and it was one that we almost included in a trial but didn't get the chance to last year. It may be one that we get a chance to trial in 2016. Okay, all I need to do finally is just give some thanks. One, Australia for funding the study I've shown to you today. The wineries involved, particularly Petaluma in the Adelaide Hills, for all their support, and the technology suppliers for their support during the trial. Thank you.
Okay, thanks very much for that, Neil. So Neil's going to stick around for a few minutes to run through any questions you have. So please start sending them through now. Just a reminder, if you do have a question, you can type it into your control panel and send it through. There's also the option of clicking the raise hand button if you'd like to use your microphone. We've got our first question here. I'm just sending it through to Neil now.
So I've got a question from Jonathan Creek asking around the opportunity for larger wineries to consider linking this data into a system that's easily monitored, as it would be a lot of data, and have we considered looking at what would be involved in terms of payback? The short answer is we haven't looked at the detailed financial position for that particular scenario, but certainly this type of data, if you can link it into a central control system and then link that up to some of the other elements that you're measuring in a winery and make informed decisions with all of the data in front of you, has the potential to be a lot more powerful than just looking at the sensor output in isolation. And I also mentioned the ferment simulation tool, which was originally developed here at the AWRI, is now publicly available. If you could link that type of system in and have the output data from the sensor included as an input into that model, it would give you the potential to actually predict where you might see problems before they exist. So that type of setup would be much more powerful. There's obviously more costs associated with linking all the systems together.
Okay, thanks for your question there, Jonathan. Still waiting on another question. We'll hang around for another 30 seconds or so and see if the final question comes through. Otherwise, we'll start to wrap up. Okay, I've got another question there for you, Neil.
Okay, so I've got a question about the scale of the red ferments that we monitored at the Bortley. They were 200 kiloliter red fermenters that we set the sensors up to initially monitor.
Okay, thanks for your questions, Stephen. If you have any follow-ups, send them through now. Okay, looks like that's it with regard to the Q&A, so I think we'll finish the session there. Firstly, I'd like to thank Neil for coming in and presenting today. Thank you also goes out to everyone who's attended and took part in the session. For attendees, you will receive a follow-up email with a link to this recording. That email will also have a link to a survey. Next week's webinar is presented by Simon Nordeskard, a senior engineer with the AWRI, and the topic is recent advances in destemming and sorting technology. If you haven't already registered for this session and would like to do so, please visit the AWRI website. And once again, thank you to everyone for joining, and please do check out the AWRI's webinar program to register for future sessions.